Newton's Law of Cooling by Juan Rodriguez and Adley Green. Topic of identify briefly introduction. The topic we chosen Newton's Law of Cooling, which basically explains how the temperature of an object changes over time when it's put into a cooler environment. It's a pretty simple but powerful idea that shows how fast something cools down depending on the difference between its temperature and the air around it. Relevant fields thoroughly described. The topic falls under physics, especially thermodynamics, which is the study of heat and energy. Newton's law of cooling is super important for things like engineering, weather forecasting, food safety, and even forensic science when estimating time of death. Relevant scientists thoroughly discussed. The scientist behind this law is Sir Isaac Newton, who was famous for a ton of discoveries in physics and math. Besides figuring out gravity and motion, he also studied how objects lose heat, which led to cooling law. Even though it's called Newton's Law of Cooling, a lot of later scientists built on his work to make it more accurate for different situations. Original experimental process described. When Newton first came up with the law of cooling, he didn't really want to do what we would call a full experiment today. He mostly observed how things like hot liquids cooled down when it left in cooler air. He notices the rate of cooling seemed to depend on how much hotter the object was compared to the surrounding air. So he put together a formula that said the rate of temperature change is proportional to temperature difference. Complications explained. One big challenge Newton faced was that he didn't have super accurate thermometers or tools that we do today, so getting really precise temperature measurements was hard. Also, things like wind, humidity, and different materials can mess with how fast something cools, and back then they didn't fully understand all those extra factors. Motivation for experiment presented. Newton was trying to understand the basic rules of how nature worked. He wanted to figure out patterns that could be predicted with math, and cooling was something else easy to see happen every day. By finding a pattern in cooling, how he could show that even something as simple as a cup of tea getting cold follows predictable rules. Original benefits of discovery discussed. At the time, Newton's law of cooling helped scientists realize that heat loss wasn't random. It could be measured and predicted. This opened the door to better experiments in thermodynamics later on. It also helped with designing things like better buildings and early scientific equipment where temperature control was important. Modern experimental process described. Today's experiment in cooling are way more high-tech than in Newton's time. Scientists now use super-sensitive digital thermometers, climate-controlled rooms, and computers to track exactly how fast an object cools. They can even run experiments where environmental humidity, air pressure, and air movement are all controlled just to make results super accurate. Difference in modern approach outlined. The biggest difference in that Newton mostly observed and made guesses based on what he saw, while today's scientists can actually measure tiny temperature changes in real time. Modern experiments are more detailed, use more data, and can even adjust for factors that Newton did not know about, like radiation, heat loss, or convection currents. Final tips and takeaways. Now, Newton's law of cooling is used in tons of fields. It helps engineers design cooling systems for cars and computers, help doctors in forensic science to estimate the time of death, and even helps food scientists figure out the best way to chill food safely. Having exact numbers for cooling rates making a big difference in all these areas. Future expectation of research discussed. In the future, scientists want to make cooling predictions even better by combining Newton's idea with machine learning AI. That way, they can model really complicated situations like how spacecraft cool down in space or how new materials react to extreme temperatures. Basically, Newton's simple law is still evolving and helping with brand new technology.
Newton's law of cooling describes how fast an object cools based on the temperature differences within its surroundings. This idea is useful in real life, like figuring out how fast your coffee gets cold. Benefits of understanding Newton's law of cooling. Predicting cooling or heating time helps estimate how long it takes an object to reach room temperature. Forensic scientists use it to estimate the time of death by analyzing how a body cools. And engineering and design engineers use it to design cooling systems. Environmental control used to model temperatures in rooms. The process of writing question outlines for Newton's law of cooling describes how the temperature of an object changes over time as it moves towards the temperature of its surrounding environment. You have to explain the principle at which the rate of an object cools is proportional to the difference in the temperature between the object and its environment. Then write the differential equation form, provide the general solution, state the assumptions, and show practice examples. The following shows relevant formulas explained in Newton's law of cooling. Solving process described for Newton's law of cooling. The rate at which the temperature of the object changes over time is proportional to the constant. To solve the equation, aim to isolate the variable t, then rewrite the equation so that all t terms are all on one side. Once you get all t terms on one side, you get a linear function of time. Now you simplify the equation to make t the subject. Then you get an expression. For an example, if the object starts at 90 degrees and the room is at 20 degrees, you plug those values into your formula to figure out the constant that completes the solution. Now that you have a complete equation describing the temperature over time, you can plug in any time t to see how the temperature has changed. For example, after 10 minutes and 30 minutes. Solution for Newton's law of cooling. The description separates the variables, solves for t. The temperature differences between the object and environment isn't too large. Heat transfer is primarily by convention. The object is small or uniform enough for its temperature to be treated as its constant throughout. Additional information for Newton's law of cooling includes forensic and crime-solving and food industry regulations. Forensic scientists use it to estimate the time of death when a body is found. Investigators can use it to measure the temperature and compare it to the ambient temperature to estimate when the person died. The food industry to ensure cooked foods are cooled down properly. Even though Isaac Newton is most famous for discovering gravity and the laws of motion, he is also known for inventing calculus, and he built the first reflecting telescope. Newton worked on his theories for decades. His ideas on heat and cooling were published around 1701, but they were based on his years earlier experiments. In Newton's time, scientists didn't use Celsius or Fahrenheit. They used vague terms like degrees of heat and handmade thermometers. The math behind Newton's law of cooling came from before most people had reliable ways to measure temperature. Additional interest describes. One of the most surprising things we discovered was how often Newton's law of cooling was still used today, especially in unexpected fields like forensic scientists and food industries. We didn't realize that sometimes something developed over 300 years ago could still be used in modern criminal investigations to estimate time of death. It was also interesting to find out that while the laws seem so simple, real-world applications are much more complex due to factors like wind and changing temperatures. Newton's law of cooling describes how the temperature of an object changes over time when it is placed in a different temperature environment. It states that the temperature at which an object cools is proportional to the difference between its temperatures and the surrounding ambient temperatures. This creates an exponential decay and temperatures over time. The law represented by the equation or its solution. The principle is still used in today's real-life applications like forensic science, food safety, and engineering. We learned that while the formula is simple, applying it accurately requires understanding real-world factors like insulation, airflow, and changing temperatures. Newton's law of cooling shows how classical physics can still help us solve modern-day problems.